I think this stream should be live right about now. If not, please notify me in the Slack chat. You can also notify me if it's actually working, so I know that. Mixed. So today we will focus on modeling to prepare you for the assignment, and also talk a little bit more about what models are and what modeling is in software development. You will also learn some UML as an added bonus. First, any questions from last session or from the requirements part from last sessions, the week of work or stuff like that? Feel free to scream out loud. Otherwise, I will kind of like just go for it. Yes. So, models, what are they? More or less a way to explain or understand reality used in everyday life by every one of us. We kind of like have models in our head on how life and reality works, and we make predictions based on these models that are very often true and functional. However, in reality, in the natural world, stuff is really complicated and really detailed. So understanding all these details and complications is very hard, and we need models to be able to work with reality, to make predictions of reality. What will happen if I drop this glass? What will happen if I throw this up in the air? We have models for everything of that. So when doing kind of like everyday life, we use our mental models to cope, and we realize that I don't need to know every little bit of detail of everything to kind of like work with these models. They can work without all these complex details. So the fundamental aspect of model is that they remove details that we don't need at the moment. So models are good enough versions that can be used in a specific situation. So it's important to realize that some models do not apply in all situations, or most models do not apply in all situations. The classic example is Newtonian mechanics. You know the stuff you learned in high school. When you drop something, it falls and it has a certain force and gets a certain velocity, and so on and so forth. How do masses interact with each other? This is a model that works very well. We can make very good predictions based on these models to construct things, for example. However, if stuff moves really fast, the classical mechanics do not work anymore. So we had more complicated models to deal with those situations. If stuff is really small, classical mechanics do not work anymore. The predictions they can make are not accurate or simply do not work. So we have other models in that case. And if things are small and move very fast, we have yet other models. So it's important to know what situations the model actually apply to be able to use it, because using the wrong model in the wrong situation will not give good results. The point is, we all use models all the time. Most of the time they are fit for purpose, but we need to know when the models are fit for purpose and when they are not. And reality, the natural world, is infinitely complex, and we have not yet understood it, and maybe we will never understand it fully. That was a little bit about models in general. Software system models, I've chosen to divide them in two basic flavors. He talks a little bit about this in the book. We have formal models. Formal models can be used when specifying a system, when developing a system, and when making sure that the system works as intended. Formal models are often based on some kind of mathematical construction. So using formal models, we can basically prove that our system will behave as it should. And we can use these mathematical models to find problems in our specifications, to generate our implementation, and really know that this system will work as intended. Sounds good, right? Should be super nice to be able to mathematically prove that your program will work. Very nice, however, not so easy. Quite complicated, actually. Even though research has been trying to do this for quite a while, and we have come some way, it is rarely used in the everyday life of the general software engineer. My guess is that you will not use formal models at all. Very few of you will use formal models. So they are used for very important systems, of course, like control systems for important facilities like nuclear power plants and stuff like that. Can also be used in really low level and fundamental communication protocols and stuff like that. The things that we really don't want to break. Things that are really important that they work. We can use formal models for that. Because it's hard, it's possibly even more hard than actually developing the system to make all these mathematical proofs that stuff actually work. It requires a lot of detail. And we need to give these theorem provers a lot of information for them to be able to work. But stuff is happening. Research is going along in this area. So it's very important to have at least a basic understanding that this exists. And it can be done. It can be very important in some circumstances. But as I said, I don't think that you will really face these formal models in your everyday work. And maybe a few of you will. What you will face, however, are informal models. And we use informal models in software system development to specify. We use them to find problems in our specifications. We use them to find improvements to our specifications. We use informal models when developing software. To divide work among many developers, for example, to have some kind of general understanding of the parts of our software system and how they will interact and how they will work together. And we use informal models to improve our testing activities, to find the weak spots in our software, to know that we have exercised all the paths in our program or in our specification and things like that. Maybe this can be thought about more kind of like of some kind of blueprints over the system. You know, like in mechanical engineering, they use models of materials and stuff, so they know how big they need to make the beams that will hold the bridge. So they use mathematical models for that. And based on these calculations, they derive a blueprint. So they have quite a firm connection to the mathematical side, the natural world, so to speak, because we have gravity and we have all these kind of like physical, natural phenomena that they need to take into account. In software, we do have some stuff like that, but we are more geared towards using models or blueprints as a communication aid between different stakeholders. So to be able to communicate with your fellow developers, to be able to communicate with the end user and customer, we can use these sketches or blueprints or models. So we don't really use these mathematical models founded in natural science if we use informal modeling, which is what you will actually probably face. So we do visual modeling, we do sketches, and as I said before, you all get a mental model of the problem that you solve. Even if you do not write it down on a piece of paper or something like that, you have a model of how the system works in your head. Sometimes it's beneficial to put this down on paper or a whiteboard or in a tool. So, as I said, we use informal models for specification, and we use them to understand the requirements, to analyze stuff, to know who does what information flows into the system, what information comes out of the system. We try to find the problems in our requirements as early as possible, so we can use visual models to understand that, well, this flow of events could be improved in this way, or we have forgotten to think about this, or this part contradicts what this other part says, so how should we resolve that? We can use models for understanding this. We use models during development, more or less like blueprints of the system, to coordinate and document how things work, how things is supposed to fit together. Depending on the type of project, these blueprints can be really blueprints, very detailed. They can be handled with care. If you are many developers, maybe distributed over many locations, you need to kind of like have a firm grasp on who does what parts is the system made up of, how should these parts communicate. If you're 5 guys in a small room, maybe your coordination and documentation will be more in the form of sketches on a whiteboard, sketches on paper, discussions. You can share this mental model that you have over the system more easily if you're a tight, small bunch of developers. And then maybe the kind of like big blueprints are not that necessary. These structures, these ideas, these models of the parts of the system and how these communicate can influence quality of the product. So we can, for example, design for performance, we can design for security, and we can design for reusability, and we can design for maintainability, changeability, and so on and so forth. So it can be really important to define the structure in certain ways to enable these quality requirements, or at least not hinder them. And this is called design. That is, how will the system work? How will the parts interact with each other? For verification, we can use these blueprints to understand where the system could be vulnerable, where it was probably hard to make the implementation, and we can focus the testing efforts on these parts. So we can more effectively test the system. So in the book he talks about 4 model perspectives. The first perspective is to put the system in a context. That is, what other systems do we communicate with? Do we rely on? What other systems rely on us? What people rely on us? What people use our system? You have actually seen a small diagram for this already if you take a look at the assignment and last session, we can see that our system offers the start game service, the play game service, and the quit game service, and we are used by a gamer. So we have put our system into some kind of environment, even if it's very, very small in this case. Go, gadget copter. Let's try again. That was odd. Alright, we will do it like this then. The next perspective is interaction. To know what input and output sequences there are to achieve some kind of functionality. This could be from a user and system perspective, or more detailed, some kind of component to component perspective. And I put component in kind of like this quotation marks, because it's component is a word that's used with many different meaning, and in this way it can mean more or less anything. You have seen this also actually in the form of the use cases that we have. So in the use case we have a interaction perspective. We write down the sequence of input and output. Even though it's not a sketch or boxes and arrows, it is a model, an interaction model, but it's written in text instead of being visualized. We have the structural perspective. What are the components of the system, and how do these components talk to each other? What are the relations between these components? And finally, we have a behavioral perspective. That is, what state and what transitions can occur in our system or in a component in our system. Let's see if Google wants to play. Yes. So, interaction modeling based on use cases is a good starting point, and maybe one of the advantages of using use cases is that they are actually models, and they are quite easy to visualize, as we will see also. If you remember, we have our scenarios, the text, the input and output statements that we wrote down, and we started with this happy day scenario where everything works as it should. The user makes all the correct choices and the system answers as it should, and this forms maybe the first scenario in our use case, and we then later extend this scenario with different choices the user can make, error situations, and stuff like that. So a scenario is basically one path through the use case that achieves some function. And to visualize this, we can use the UML activity diagram. And by using the UML activity diagram, we can see the scenario steps in relation to each other, basically what can happen and who are involved. So we have here a small use case, or maybe not that small, it's quite long. It's a system for e-commerce, and it's the return item main scenario. And basically we have the trigger first. The customer wants to return a delivered item. Our system contacts an order system to get the customer's delivered items. Does not make sense to show a list of undeliverable items to the customer, so we need to find out what has actually been delivered. This order system, as it should say there, returns all the delivered items, and our system presents the customer with the items that can be returned, selects one, we show the item and order details, selects the reason for the return, and we show an overview of the item selected for return. And we can also go back to step number 2 if we want to return other items. And finally we confirm the return, and the system initiates the return item procedure and informs the customer on how to proceed and print a return slip. Basic kind of like flow of events. Everything turns out as it should. And we can visualize this using an activity diagram. And in this case it would look something like this. So basically we have 3 actors involved here. We have the customer, that's the primary actor. He or she uses the system, starts this interaction. And we can see that by the big black dot there. That's the starting point. If you look to the down, you have a bullseye, and that's the goal point or end point of the interaction. You can remember those symbols. They will kind of like come up in other diagrams also. Then we have a lane for the system, what the system does, and we also have a lane for this supporting actor, the order system, what it is supposed to do. And we basically map the steps of the use case to the different actors, and we map out the flow between them. So step number 2, we contact the inventory system or order system, and the order system gets the returnable items. Our system presents the items, the customer selects an item, we show the details, we select the reason, we show the overview, we confirm, and we have this option to go back to step number 4 and present the items again, or initiate the return procedure, and we are done. So in this way we can get a feeling for visualization of the flow of events in this scenario, and we can see when and where we need to communicate with either the primary actor or the secondary actor, supporting actor. We can see the places where things can branch and do different things. So it's quite a nice visualization of the use case, and maybe we can find some improvements here. If we rearrange the steps in this way, maybe the use case will become better in some way. You can also see that we have kind of like made a decision here to contact the order system only once. Maybe this is because of performance reasons. Maybe it's just happened to become this way, but we can clearly see here that we need to kind of like remember the returnable items as it is right now, and so that we can present them again if wanted. This could be a good choice, could be a bad choice, but it's something that we can clearly see right now anyway, that we have made this choice anyway. Okay. Nothing funny or wonky about that. So this was one scenario, and we continue to build on this model by extending it with our alternative scenarios also. So maybe our customer does not have any returnable items, or we get some kind of an error code or error message from the order system. What should we do then? Well, we have decided that we should try to get all the orders from this order system instead and do something else. And we add this to our activity diagram, and it will of course become larger and larger, and we will see kind of like how the scenarios play into each other, how they are connected, and find the different paths that can become valid in different situations. And this can be used to both improve the requirements in itself by rearranging these steps. Maybe we can find a more efficient way of doing things, more user-friendly, more efficient in contacting this order system. Maybe we can use it to understand how things need to be tested. We need to kind of like trace every path so that we can know that we have tested every path at least once. So we can use a model like this in different ways. Can you see any downside to using a model like this? If it's only good, everyone should do it, right? All the time. Well, in general, all these informal models have one big problem, and that is that they need to be maintained. So when something is updated, you need to update these models also. So if I rearrange the steps in this activity diagram, I need to update the use case specification, right? Or if I update the use case specification, I need to update this activity diagram. So we need to keep these models synchronized to some degree. And this is true for basically all of these models, because some models will be models more or less over the implementation, the structure, for example, of the implementation. But when you program, maybe you do something else. You realize that, oh, we cannot do it in this way. So you do the implementation in a slightly different way, and you are 50 people on the team, and everyone does some things a little slightly different than what the blueprint says. And over time, the real implementation and the blueprint will not say the same thing. So that is a major downside of modeling, especially if you do not have good tool support. So in the best of worlds, of course, when I update this activity diagram, when I rearrange the steps, maybe the use case steps are automatically rearranged also. That would be super neat. Or if I rearrange the steps in the use case, they will be automatically rearranged in the activity diagram, or in the or added to an activity diagram. So having kind of like tool support to keep the different representations of different things in sync is something that is dearly needed, but have not really succeeded in a major way at least. So that is something that you should keep in mind. If you use models, think about what you need them for. Do you need them for this moment? Do you need to save them? Should you maintain them? you probably at least need to add some kind of a date to them, so you know when they are valid, when they were valid last. You need procedures to update them if you need to keep them updated. And one thing I said yesterday was it's quite easy to forget things. So you work on a part of the system and you understand this part really, really well. And then you leave that part to work on some other part of the system, and someone finds a bug in the first part, and you need to go back and try to understand what you did 6 months ago. And you will be surprised how fast you forget, and how you will feel often like an idiot when you look at your old code and just, what was I thinking? Why did I do it like this? Why are these two parts connected? So it can be a good idea to actually save these models, even if they are informal, and have them as a mental cue to get back into old parts of the system. But do remember that maybe someone else has been in that part of the code also, so your model may not be valid anymore. So tools to reverse engineer, to keep models in sync, is something that is needed, and you should always look out for that. So let's go back. So we have done some interaction modeling. We have done it based on use cases. We used the UML activity diagram. We could see the scenario steps in relation to each other, and we could see who does what and who are involved in the different scenarios. Another way to use use cases as a base for modeling the system is to do use case realizations. In use case realizations, we look inside the system instead. So we take a look at the parts of the system and how they will collaborate to achieve the functionality of the scenario. Basically, yes? Ooh. Jag har nog fel. I got the wrong selection. So the activity diagram shows exactly the same thing as the scenario. Well, basically the same thing. It shows at least the flow, the exact flow of the scenario. Activity diagrams can be used for other things also. They can be used for visualizing algorithms and stuff like that. But they can be used for this type of interaction modeling based on use cases. All right. In the realization, we look at how the different parts of the software system will collaborate to achieve some functionality. And for this, we use the UML sequence diagram. Basically, the sequence of function calls, procedure calls, method calls that must happen to get the functionality that we want. And a sequence diagram can look something like this. This is generated by using web sequence diagrams. And actually the first little box there should be this actor stick figure guy, but the tool did not support that, so I couldn't do it. But basically we have the different parts of the implementation. We have some controller, player thing. I think it's a class in this case. We have a model dealer thing. We have a deck thing. We have a card thing. We have a player thing. We have a view thing. Can you guess what kind of a system this is? Yes, has something to do with cards.
Poker game maybe?
Poker game maybe? Maybe. So it's a card game at least. It's not poker. it's a blackjack game, I think. But it could very well have been poker. And this is an interesting aspect, that by looking at kind of like the naming of stuff, you can kind of like guess what the system is about. And that's probably a good thing, right? Because you can get into the mental model of what this is about by looking at the diagram. So names are important. But here we can see the sequence of events, and time flows kind of like downwards here. So we start with the trigger that the actor wants to play, and stuff happens in sequence. Functions are called with arguments, methods, procedures, or what you call them depending on your preferred implementation language. But finally, we kind of like, we deal the cards to a dealer, and we deal the cards to the player, and we present the dealer's hand, and we get the value and the color of each card in the hand, and we present the player hand, and we get the value and the color of each of these cards. So basically, I think the steps in this use case would be like the player wants to play a new game of blackjack. The system deals 2 cards to the dealer and to the player, and show the card colors and values. And we can basically see this flow of events in the implementation quite neatly connected to the requirement. Why do you think that is a good thing? Well, we could imagine the scenario that, well, a user faces a bug, and the user says, well, I tried to start a new game, but it didn't work. Then you kind of like immediately know, all right, somewhere in this part of the system there is probably a bug, because these parts are involved in the scenario of starting a new game. So you get this kind of like traceability from requirement to implementation. And we can imagine a big system with maybe 1,000, 5,000, 10,000, 100,000 classes or parts. Being able to rule out a big part of them quickly is a good thing. There is another advantage with doing this, and it's about focusing on the behavior and the functionality that is needed right now. So we are implementing this start new game scenario, and we can focus our efforts in that. There is a real possibility and a real risk that as a developer, especially if we are a little bit more free, we spend the time on quite unimportant details. I think at least the web programmer program will have a course called Individual Software Development Project after this course. There are always, and you get to freely choose more or less the system that you would like to implement and develop. And I've been involved in this course. I probably will not be involved this year, but there are always a few students that kind of like focus so much on a teeny little bit of detail. Can be something in the user interface that they are not happy with. Oh, I want this to be another color, or moved, should be centered and it's not really centered, or stuff like that. Or it can be some obscure little design detail. And they focus so much on this that they don't do the big picture thing. They don't have a working system at the end, but rather they have maybe fixed this little detail, but the system as a whole does not work. So it's really easy to kind of like get too focused on one little part that you want to get working really well. And maybe you get it working really well, but you have spent like 4 or 5 or 6 weeks on this. And you always need to be able to prioritize. And doing kind of like these kind of models, you get to focus more on the functionality that is needed right now, and you don't think so much about adding stuff that's not really necessary. Gold plating is a phenomenon that can hinder you more than give benefit. Sequence diagrams, UML. I don't know if you know about the UML. Do you know what it is? Some do. Unified modeling language. It's basically a standard on how to draw different types of diagrams with a common notation. Before we had the UML, we had the language wars. So different bearded guys did different types of boxes and arrows, and finally they agreed on how to do boxes and arrows, and the UML was born. It's managed by a group, object management group, so you can find a specification for it. It's quite detailed. There are many aspects of this language, and it's really a language if you want to go into that. But for informal models, we kind of like relax the standards a little bit, and we often need to work with the tools and the notation that the tools kind of like give us. So notation wise, it will not always be perfect, but it will be good enough for the purposes that we have. But you can look into the UML and the UML standard, and we will try, of course, to do our best to follow the standard. And it's a good thing, because this means that you can look at the diagram from someone else and you can understand what they mean with these arrows and boxes. So it's a common language that we all can use. And you can also see here that we can do kind of like loops and stuff in this sequence diagram, and it's quite close to the implementation. All right. I think it's time for a break, actually. Any questions so far? No? Right. Let's take 15 minutes of a break then, and we will talk about state machines for the next part. right maybe now. I was a little bit fast there maybe. So basically the first task on the assignment is about doing the use cases and the use case model. And you will get a starting point, the basic hangman use case diagram with 3 requirements: start, play, and quit game. You will also actually get the scenarios for start game and quit game, and basically it's about starting the application and being able to quit the application. And you will write the fully dressed use case for the basic version of the how to play the game in this part. And start with the basic version, and for a chance to get a higher grade you will extend this use case maybe, or maybe you have other use cases that you would like to present, depending on your vision. So start with the basic one so that you have some foundation to go back to if time runs out, and then you do the extended versions. Task number 3 is about modeling the behavior of the system. And here you will be presented with a new type of model that we have not spoken about yet. You will do a state machine. I don't know if you have faced state machines before or are familiar with them. Basically, it's a theoretical kind of machine that has different states. It can be in a state, and depending on the input to this machine, it can move from this state to some other state. And this means that it can react differently on the same input, for example, depending on what state it happens to be at the moment. A simple way to think about state machines is to basically think about everyday machines that we use. For example, a coffee machine or something like that. Depending on the input we put into it, we get different things out, and it kind of like moves between different states of boiling the water, grounding the coffee, mixing the milk, and whatnot. And you will also get a basic state machine for the hangman system or application or game, based on the requirements that you have seen before. So we start again at the black dot. This is the starting point. And the first thing that should happen is that we should present some kind of a menu, and then the machine waits for input. Depending on the input, we can either start a new game or we can terminate. If we terminate, we wait for a confirmation. If we get a yes as a confirmation, we have reached the goal and the state machine has terminated. It's over. The application, we have quit the application. If we say no, we go back to the present menu state. If we start a game, we should be able to end the game and go back to the present menu state, or we should be able to terminate the game and go to the confirmed termination state. And if we select no and come from the play game state, then we should be able to go back to the play game state. So if I play the game, I enter 4 characters, I realize it's time to eat, I terminate the game, but as soon as I have terminated, I realize that I have guessed the word. So I go back into the game, enter the final character maybe, and win. That's basically what this little state machine says I should be able to do. So this is yet another way to kind of like look at how should the system behave in different situations, right? More or less like a specification of the requirements. Your task in this part of the assignment is then to look into the play game state and make a state machine of what happens inside this state. The user can enter different characters, some things are displayed, the user can win probably, the user can lose, and different things will happen depending on the states we are in. So, state machines. Present. We can use them to specify and understand dynamic behavior. Maybe we can find better ways of doing things by looking at our state machine. Have opportunity to improve, or maybe we can realize that, well, what happens if this happens? We have forgotten something in our requirements. We can use state machines as a formal modeling technique. So there are state machines and there are mathematical theories around state machines that can be used for formal modeling, or we can do more informal models like we do in this course. And actually, state machines are one of the foundational principles of computer science. It's a thing that has kind of like been the foundation of how computers work from a theoretical perspective. And this is called automata theory, and you can read more about that if you are interested. We can use state machines to generate implementation. So we can kind of like, if we do detailed state machines, we can more or less do our whole implementation in a modeling environment and generate the code, the executable code from that. So, and basically it's a theoretical machine that reacts on events from the outside. We model this machine using states and transitions, and we can order these machines in hierarchies. So inside one state we can have a new state machine, and inside the states this state machine we can have a new state machine, and so on and so forth. So we can take a look at the high level, and we can dive into the details using state machines. So, another example. We can take a look at how a membership should be handled in our system. Maybe we have an e-commerce system based around membership and some services linked to that. So we start again at the big black dot, and we go into the registered state. The member has registered. However, if 48 hours pass, we go down into a collection state and then go to a purge membership information, and the member is no more. So the member needs to confirm the membership within 48 hours. If that happens, the membership has the state pending, and basically that means waiting for payment, membership payment. So either the membership can be cancelled, or 30 days can pass without any payment, and again we purge the membership information finally. If we pay the fee, we go into an active state where maybe the user can access different services and content maybe. The membership can be cancelled. From the active state we can also get a fee not paid event. Maybe you pay monthly, and then the membership is blocked, and we can also realize that we have paid the fee and continue to be active from the block state. Or we can cancel the membership and become dormant, and if we cancel and confirm this cancelment, then we should repay the remaining membership fee. So do you see a problem with this model? Well, if we are in dormant, we cannot actually go back to active. That's probably not a desired behavior. And also up in the left, it's called registrerad. That's Swedish and should probably not be Swedish. So we can use models like this to understand that we have forgotten something. We haven't thought about this behavior. The behavior in this state is probably not what we want, and we can find out problems like this and test drive almost the system using state machines. The basic notation is a box for the states with a state name. And a state is some kind of interesting situation during the lifetime of an object when it satisfies some condition. And object in this sense is used in a very wide sense. It's not object like an object-oriented object. It can be more or less anything. I think that you will probably have states more or less where the system or the object waits for some event. So in the state you do something and then you wait for some input from the outside. That is maybe the most common situation. When we have a state, we can have an action or an activity that is performed when we enter the state. And we specify that using an entry word. We can do the same for an exit word, so something that should happen and something that should be performed when we exit the state using any transition. We can have internal activities, internal reactions to events in the state, or we can have some activity that we perform continuously in the state also. The next part when we have the state is to define transitions between these states. That is some kind of edge or bridge between two states. And that means that we can go from one state to another using a transition. If there is no transition, then there is no way for the machine to move from a state to the other state. So in our example, there was no transition from what was it called? Dormant. There was no transition from dormant to active, but rather the member actually had to confirm. We had to repay, and to become a member again, he had to go through the entire registration procedure once more. Probably not what we want. And to know which transition to exercise, we specify the events that can happen. And to do this, we can also specify special conditions that need to apply to be able to take this event, or special actions that should happen when we transition from one state to another state. One important thing to remember is that these machines should be deterministic. What does that mean? Basically, you cannot leave things to random chance here. So from a state, you cannot have two transitions with the exact same event, because then the machine cannot know which it should take. So we model using deterministic state machines. So looking at, for example, the this little state machine, we actually have the same event from confirm termination. We have no there, and we have the event no there, and we have this guard condition to let the machine know which it should take. If I would have not taken this opportunity to specify the guard condition, then the machine would not know where it should go if it gets the no event, and that won't fly. That is something to think about in your assignments. Model using deterministic state machines. All right. My last slide is this state machine. Is this a good design, you think? Can we guess what it's a state machine for? Probably a keyboard. We have a caps lock event. That's not that common in other machines, I think. So basically what happens is we start and we initialize something. We have an action key count equals 1000. So we set the key count to 1000. We go into the default state. We can move between the caps lock and the caps locked state by using the caps lock event. So basically if you push it once, you go into the caps lock. If you push it again, you go back to the default. So we can move between these two states. If in these two states we press any key, we decrease the key count and we go to a choice pseudo state. And if the key count is 0, we go into the goal state. So then the machine cannot do anything more again. Otherwise, we just loop back more or less to our the state that we were in. So what will happen with this keyboard? It will stop working after 1000 any key events. That's probably not a good design. But we can see some interesting stuff in this diagram. We have different actions and we can specify them quite well. And you could imagine that we could kind of like generate implementation from this diagram. Basically it's variables, it's some kind of a state variable is needed. We have some if statements going on, and it should be possible to generate some kind of implementation from this, right? Or simulate what's actually happening here. Questions? Everything is super duper clear? All right, let's go back to the assignment then. So you will dive into this play game state and model what's inside of that as the task. When you have done that for the basic version, you may or may not want the chance to get a high grade and extend the state machine with other states and transitions according to your extended use case model. So do the basic version first, where you can actually just play the game, and then maybe you have ideas on how to make the game more exciting, add additional features to it, and you make a state machine for those ideas also. But do this in a separate model, so that you can always get a passing grade at least. Then you will implement the basic version of what you have modeled, and do this really basic. For example, you don't need to spend time on drawing this hangman figure on the screen. You can just present the number of attempts left as a number. It's more important to get the thing working than to get the thing pretty. You can add prettiness in iterations to come. So start with this and then go on to task number 4. That's about modeling structure, and you model the structure based on your implementation. So this is more of a reverse engineering task, to document what you have actually implemented. So the first part is more about thinking before doing. The other part is about learning what you have actually done and see what parts you have and how these will stick together. Then you may implement extended features if you have the time, according to what you did in the state machine, for example. And you can also do the reverse engineering of these extended things if they change the first version. So go for the passing grade first. If time permits, add more. We will talk about modeling structure in the next session. But basically we are kind of like doing some form of class diagram for this part. So we will take a look at the UML class diagram. Questions on the assignment? Yes? You can do several files if you want to. Personally, I probably would do that. I would probably also do the documentation in the wiki of the of your GitHub repository. You may do it as a PDF and do a release and stuff like that if you want to do that. Images, keep it to common file formats. So no wonky file formats, strange tools, stuff like that. You may use them, of course, but the final hand-in should kind of like be easy for us to look at. And you can have several files, that's fine. I don't really mind about that. So that would probably be, I would not put it in the project plan document template thingy that you have already done for assignment number 1. I would keep it separate. You can update it. So update the original document. For example, if you now realize that, wow, this new feature would be super cool, maybe it should affect the vision that you have already written in some way. So feel free to update if you want to. And of course, your planning. It would be quite unlikely that you would never update the plan, because as you gain more information about the project, the tasks, the way you work, the schedule that you have in some way committed to may change due to circumstances. It's no idea to kind of like use a plan that is outdated, that you know isn't correct. So update the plan if you need to update it. All right. So basically, you should hand in a time log with your estimates of the tasks. You should track the time that you spend on the different parts according to your estimates. And you should follow up these estimations with reality and see, well, I really suck at estimating implementation. It takes way longer than I think, and learn from that experience. You should hand in an updated use case diagram with possible new features that you may envision. You should hand in a fully dressed use case diagram for the play game use case, the basic version. And you may hand in an extended use case model that is both use case diagram and more use cases or extensions to this play game use case if you have other interesting features that you would like to present. You should hand in a state machine diagram for the play game use case and optionally an extended state machine for a higher grade. So do the basic state machine first and then possible extensions. You should hand in the implementation. I hope that you already have it under source control, and you should do a class diagram based on this implementation. That's about it. For the next session, feel free to send me any questions, or you can send your diagrams and we can discuss them, or you can send requirements and we can discuss them. So doing the class diagram session is quite a short thing, I think. If I stretch it out, we can talk about structure maybe 45 minutes or something like that. So feel free to fill the other 45 minutes with your questions and ideas for the assignment. All right? Anything else? Oh, good. I'm available on Slack. I will answer any questions if they are not already answered by the tutors. They are quite efficient, it seems. So, but feel free to send me your stuff on Slack, and I can incorporate them anonymously, of course, in the next session. All right. That's it for now. Thanks. Stop.